into that detail, a couple of things I want to show you based on the last section, the question. Let me share screen. I have so many things open here. Can you see my slide?
Yes, sir.
Yes.
All right. So I only show you the schematics, the flow diagram of the microwave and also the microwave plasma. So this is the reactor. Okay. So you haven't seen the picture of a reactor. So typically in a laboratory, this is what we have about 8 years ago. So this is what we have is a microwave reactor. So you can tell it's different from what you use at home now, right? This is really the no different from any your laboratory like a thermal catalytic reactor. So then in 2009 we developed this catalyst, and then you can see that it's a tubular reactor. It's not. I want everyone to throw away that microwave is a box. Just only because of you use a microwave oven at home. A lot of people think, oh, microwave reactor is in the box. No, it's not. And look at it today. We scale up the reactor. It's a flange, and then it's a high pressure reactor. So they're no different from what they use in industry. Okay, the microwave can scale up just as if in a chemical petroleum refinery. Look at the from 2017 what we have in laboratory small scale, bench scale, and we have this pilot scale. Now we are basically scale up to the large scale. Okay, so just give you the visual impression. Microwave, they're no different when you scale up, no different from those reactor you saw in the chemical plant or petroleum refinery. So I think next session I'm gonna talk about how we use DFT to design catalysts. I'm not gonna go through this slide. Last session I talk about economic. I think one of the students asking, hey, how you do this the simulation cost estimate. For example, I use I simplify the cost estimate, 0.6 rule, but I said that's very rough. That's really rule of thumb. If you look at this slide, that really shows how detailed we conduct the economic analysis. So basically, what we do is we basically do the Iceman simulation. If you're familiar with Iceman Plus, then we have all of our assumptions: how much the cost, economic, utility cost, and everything. Remember, we have seven cases. All those cases are described in here. Some cases called cryogenic, some kind of even membrane. Remember, when you lower the pressure of the process, you can use a different technology. Then we have a thermal temperature swing absorption, and all 7 cases are listed in here. It's very detailed, but behind the scene, each absorption you need to have kinetic data, which means how fast this technology can condense the ammonia. Those are data behind. So we roll that into Iceman simulation. That's how we come up with this economic analysis. I show you the table, right? Remember that table? Show you the how we compare with the base case 1 and 2, and then now we basically have the different cases. So yeah, anyway, it's a very complex economic analysis. I think there's one section on day, I forgot which day. There'll be economic analysis. I probably talk. Yeah, on day 8. There's a technical economic analysis optimization. I probably will go through a little bit deeper on how we do the break the process into different unit operations, and then I'm going to interpret this pie chart. So why microwave electrochemical do we save the money? Where are the savings? Okay, so by basically doing the step by step, you will see that. Okay, all right. So this is really high level. I'm gonna go through the next section. Okay. Any question here on the economics? I promise you we will go through the detail on day 8. Okay, so there will be a lot of the technical economic analysis, how we build each individual unit operation. But I don't want to show you how we are going to run ISPEN. So it's a lot of work to learn how to run ISPEN, but I want to show you how you build the unit operation and why the unit operation is in there. For example, why the downstream we have a different scenario like a cryogenic generation membrane and TSA. TSA means a thermal swing operation, a thermal swing absorption. Okay, so I'm going shifting to the next one. I think let me see where's my cold plasma. I just have so many things open here. I need to close them. Just let me know when you can see the slide. Okay, I'm going to share my screen. Can you see my screen now?
Yeah, yes, sir.
Okay, application for the plasma in ammonia synthesis. Okay, so the first I want to show you how I still remember one of student mentioned about the lightning. So lightning, wow, that's one way to think about the plasma. So if you look at this, the different way to use the plasma. Okay, so if you look at the center, let me get my pointer. If you look at the center of this is the diagram. So the cold plasma, I'm going to interpret the cold plasma. Okay, so basically you see nitrogen under the cold plasma, you can make an NOx, which is called a NOx, and then you hydrogenate NOx into ammonia. That's one way to do this. Actually, there's a company in California. They are doing this route. Okay, that's one way to do cold plasma, but you have to turn N2 into NOx, which means you operate on an oxygen, make NOx, and then you hydrogenate into ammonia. So another way you see it on this side is called cold plasma direct synthesis. Direct synthesis means there's no NOx get involved. You have nitrogen, you make ammonia. Okay, so there's another way to make the ammonia using the cold plasma. So there's a different ways of plasma catalysis. Remember, I showed you the last session. In our case, we use the what you call that microwave plasma. Okay, so microwave plasma, you need a catalyst. You generate plasma, and then you have the nitrogen landed on the catalyst. Then you can produce the ammonia. So and also it's all gas phase. It's gas solid reaction. Okay, here is also gas solid reaction and the gas solid reaction. But there's another scenario. You can do this in the bubbling, the liquid phase, which means you have water and then you have nitrogen, but you also generate plasma. You can generate plasma in the liquid phase. If you see this pink color, that's the plasma in the water phase, and then you can produce the ammonia in that way as well. But in that case, you do need to bubble the hydrogen through the reactor. So the different way to generate what you call that plasma and make ammonia. So now you may be wondering, hey, in the middle case, when I have NOx, how am I going to produce the ammonia? Oh, you can hydrogenate, but true, hydrogen gas costs you money. But there's a different way. You can combine plasma with the electrochemical process, which means use the plasma to generate the NOx and SOx and putting that into the electrochemical cell. Then that'll be hydrogenated into the ammonia, but that hydrogen coming from electrolysis. So it's not going to be free. So you have to have electricity and then generate the hydride into a in addition instead of the H2, and then you hydrogen make ammonia. So a different approach to do this, but the key is if we want to the so-called decarbonize the the industry, so you have to make ammonia and using renewable power. The whole process doesn't have any carbon. So this is really the beauty of the plasma chemistry. I mean, cost. You may be arguing, oh, they cost too much money. Let's put the cost on the side. But all this the technology, there's no the carbon involved, right? So you produce ammonia, and the ammonia is energy carrier, so you can use for many other applications. Okay, so are we clear on this diagram before I go to the detail on each scenario? Any questions?
Sir, we understand the types of different types of plasma enabled ammonia synthesis, sir. But in deep also here you all process talks about nitrogen fixation only. What about here? Hydrogen is not involved in only one method, plasma bubble synthesis. We are directly passing nitrogen plasma into it. Remaining processor, we are not talking about hydrogen evaluation. We only talk about nitrogen fixation.
Yeah, well, that's a good question. So in this case, okay, I'm glad you asked this question. You are talking about hydrogen evolution. I'm glad you asked the same question. So basically, here's the cell. If you remember, maybe I should go and find that okay, let me go back and find that cartoon. So yeah, okay, let's talk about hydrogen evolution. But in this case, hydrogen evolution may not be that much critical because the NOx is very reactive than N2. You follow me? I will go back. Okay, very good question. So I will come back to here. Let's go back to my I think it's day 2. I need to find my day 2 the slide. Yeah, it all depends on your reactant. Here you are hydrogenating the NOx, and then in the previous case you are not just hydrogenating NOx, you are reacting with the N2. That's caused a problem because you need a lot of voltage to fight with hydrogen evolution. Hold on. Okay, I am looking for my. I think it's day 2 microwave overview ammonia synthesis. I want to find out in the cell. Okay, so very good question. I'm gonna share this. All right, so if you remember, now see the note I put in here, hydrogen evolution, all right? Now, in this case, you do have electrolysis, okay? And then you have the hydride going this way. But look at it on this side, what's coming into here? It's N2. N2 is very stable. It's not reactive. That's why in order to have N2 reactive with the hydride, you don't want the hydrogen coming out this way. Okay, the hydrogen. Let me put my pointer. So there are competing processes. The nitrogen on this side, your ideas have the hydrogen. It's not hydrogen. It's hydride generated passing through the membrane right with N2. All right. So what you need to avoid is H2 coming out this way. So that's why you need it's called hydrogen evolution. You need the power to fight. It's called over the potential to push H2 back into the solution so they can go this way. But the key is when hydride come this way, you have to have a nitrogen react with hydride so they can drag, keep on pulling hydride going this way so that hydride will not go into gas phase. So that means you need molecule on this side very reactive to pull the hydrogen or hydride to the right side, all right? But unfortunately, N2 is so stable, it's very difficult for N2 to react. That's why hydride, instead of saying, okay, you are not reactive, I'm going to go to gas phase. Now, if you have a NOx coming this side, the things will be different. Okay, so if you have I'm going to write it down. So if you have a NOx on this side instead of N2, so basically NOx is very reactive because it's NOx. It's easy to react with hydride. So the pulling force to this side is much greater. So you don't need too much over potential to keep the hydrogen inside here. You follow me? So I hope I interpret this to you. So reacting with the N2 in the electrochemical is very challenging. Okay, but reacting with the NOx is relatively easier. Okay, so I'm stop sharing here, and then I'm going to go back to to here. So that's why this process, because you are feeding into here the NOx, and then it's much easier. It's very reactive than N2. So that means the hydrogen evolution. There's still problem hydrogen evolution, but it's less problem compared to you feed into the N2. Did I answer your question? Is that what your question? Hydrogen evolution?
Yeah, yes, sir.
Okay, so this diagram is very good. So I really like this diagram. It's very illustrative, telling you how you utilize this, either cold plasma or plasma to drive reaction. You can directly make the ammonia. Well, it's a challenge. Nothing is free, all right? Because the N2 has to go in there. But if you have N2 going into intermediate NOx, then going to ammonia, it's pretty much the easier because you simply oxidize N2, and then because we all know N2 can be oxidized in NOx, all right? That's how that's the basic combustion. When you drive a car, the exhaust state has a lot of NOx. NOx is given, but the trouble is to hydrogen NOx, you need a lot of work. You need a basic electrochemical process. Okay. Now I'm going to pose you a question. I think Dr. Anand in a different session mentioned about the non-thermal plasma or cold plasma. Can anyone tell me what's your understanding of non-thermal plasma or cold plasma? You give a try. Anybody can give a try. So what is the non-thermal plasma or cold plasma?
Yes, sir. So non-thermal plasma means it's a cold plasma, a low temperature plasma, or a non-equilibrium. That means that when we are sending the electricity through the gas, so that the gas becomes partially ionized, so that the electron will be take up the energy of the electricity that we are giving, so that ion and gases, other radicals will be having lesser energy than the electrons. So there will be a temperature difference or energy difference between the electrons and the other heavy particles. So that we can call it as a non-thermal plasma. Plasma is nothing but a soup of positive charged ions and negative charged ions. So in that electrical electrons will be having the higher energy than the heavy particles. So that is what the non-thermal plasma.
Okay, thank you. So basically, if you have very good, okay. So that's why they call the non-thermal plasma. So basically if you have N2, you kick out one electron, so they become plasma N2. It could be N2 star, could be N star. So whatever you name, but it's plasma. There are a lot of electrons floating around. Okay, so electrons pretty hot. Electron, I think the temperature can go to if you read the literature, electron the temperature can go to I think somewhere 1400 K or to maybe the I would someone even say the tens I would say the 10,000 K. 10,000 K. I whatever the unit you name. I'm not good in Kelvin. That's the temperature. Okay. So it's very high temperature. But keep in mind the molecule, the electron, the mass or the mass of the electron is very small. All right. But the main body of the molecule is the so-called N star or N2 star. The majority of the mass or the molecular weight is on the N2 or N2 star. It's not on the electron, all right? So what does it mean? That means in the system, you have a lot of hot electrons floating around, which is good. They keep on activating the molecule, but the remaining things is basically it's cold. It's cold. That means if you apply the voltage on the, I'm going to show you a diagram. If I apply the voltage in the catalyst in there, so the reactor is not hot. So basically, right, that's why they call cold plasma, because the main body is cold, only electron floating around. It may warm up a little bit because the electron still carry some mass, but it's not hot enough. Okay, so typically for the cold plasma, if you want to drive the reaction, you need external heat put in here to make sure that you heat catalyst to the temperature, because you want overcome the activation energy. Okay, so that's the differences between the hot plasma and cold plasma. The hot plasma means you can make this the body, this species very hot, and then that's why the microwave plasma actually the by itself is pretty hot. They can heat them they can heat the catalyst, but cold plasma you cannot heat the catalyst. You have to have external heat to heat plasma. So to heat the catalyst. But the key is this electrons were hot. That's good because this electron keep on heating the neutral molecule and then kick out electron and then become activated. Remember, we were talking about the activation energy. I'm going to draw a diagram. So basically the activation energy. So this is basically the any reaction. If you want to happen, you have to overcome like this. So this is basically N2 and then H2, right? So then you end up with NH3. So without catalyst, you got to overcome hurdle. So with the catalyst, you basically your starting point and end point the same, all right, thermodynamically. But kinetically, you have to overcome here. That's why you need a temperature. But with the plasma, so if you have a plasma, you basically begin from here. So basically, you are not dealing with N2, you are dealing with N2 star plasma and H2 star. Okay, so that's the difference. Now you see, because you are the pre-active molecule, you basically you are jump start. Okay, so that's why your energy barrier is low. So it's different way to activate. But if you have the plasma and the catalyst, you base starting point in here. That's why the most reactor. So this called most reactor in plasma, they have a catalyst in there because you want to lower, not a starting point here, you want to lower the activation energy. Make sense? Okay, so, all right, so I'm going to stop here. My notation, I need to disappear. Maybe I'll stop sharing. So we'll share by. Okay, so that makes sense, all right? So I'm going to stop my annotation, and then I need to come back to what I can write. Huh? You won't allow me to create. Okay, let's do this. So if you look at it's called the DBD. So I'm pretty sure the Dr. Anand talk about how you generate the plasma, how you run the DBD type of reactor. Okay, so DBD means dielectric. So DBD means dielectric barrier discharge. Okay, so but a different way to generate plasma. DBD is the most popular generation. As I mentioned, you can have the different way to generate plasma. There's another generation called corona discharge. Corona discharge means the key is any cold plasma, you need voltage. That means as long as you keep voltage in between the gap, doesn't matter it's a solid catalyst or the empty tube, or you have basically the water phase and the water bath, and then you have this called the needle electrode. So in between this needle and the water phase, you can see the sparks. That's plasma. There's another way to generate plasma. It's called one is called DBD, that's coronal discharge. The other is called the gliding arc. Gliding arc is kind of a little bit tricky. So they have something basically spin around, and when they spin around, there's a torch shape of the plasma. It's more like it's more uniform than either coronal discharge or DBD. DBD, and it's kind of you have sparks everywhere, and then it's not uniform. It don't depend on the location of the space in here. Same with this the corona, because it don't depend on how you design this needle electrode. And then on the surface, somewhere you see the lightning strong, somewhere that you don't have what you call that plasma. But if you look at DBD, this torch shape, they can actually spin, and then it's supposed to be more uniform. It's called gliding arc. It's a different technology, but there's a different way to scale up. So now here we are talking about microwave. That's what I'm talking about, the microwave. So microwave is different. Microwave, basically you have a field or electromagnetic field basically moving around. You don't have to touch this is the reactor tube. You just have a field moving in and out. It's different from this one. This one you have to have a gap to generate plasma. But the microwave you don't need a gap. As long as you have the microwave passing through the it's called a cavity, you can generate the plasma. Okay, so this one called this is basically very typical the plasma. But if you have a cavity and then all the it's called what you call that post plasma, you can put your catalyst or some material at the edge of the plasma, and the plasma will interact. This is very popular, called afterglow, the plasma. Then the plasma can be generated by the so-called the microwave or by radio frequency. So microwave, remember microwave, the frequency range from 300 megawatt to the 300 gigahertz. But radio frequency, anything below 300 megawatt to probably 10,000 to 10,000 hertz, that's radio frequency. But radio frequency and the microwave, they are generated differently. Radio frequency, you need to have an antenna. So antenna, you basically have a power introduced and the plasma generated. Okay, so the different way to generate plasma, and then but they are different from the plasma generated has voltage. In my laboratory, I try to have a cold plasma, then I move that to the material science. The reason being that you need to be careful about the DBD plasma, because you need a 10,000 or maybe 30,000 high voltage. Anytime with high voltage, you need to be careful, because in my laboratory, I'm sure in your university, you have a graduate student postdoc. So the different from industry. Industry is pretty safe, because in industry you work in the environment, and then you have a lot of safety. But in the laboratory, my students try everything, so I don't want them to get a shock. Okay, so if you have high voltage, you got to be careful. You have to be grounded. But if it's not grounded, it's very dangerous, because one shock, you can basically it just depends on size of your voltage or the size of reactor. Some reactor is miniature, it's okay, you get shocked. But if a big reactor, there are a lot of safety features in there. But microwave, we don't have that problem. Microwave, I'm using like 110 volts. because in US the voltage is 110. So you plug in the wall, you do the direction, There are no the so-called safety issue. It's pretty safe. True. You worry about the microwave leakage, but that's very minimum. I mean, you use microwave at home, all right? You wouldn't have that microwave leakage problem. So anyway, so this is really cartoon. Before I move on to the next, I want to know if everybody understands this is the microwave scenario. Oh no, a plasma scenario. Any question? Go ahead.
Sir, understand, sir. What you explained that we understood, sir.
Yes.
On our yesterday discussion and today's discussion, yesterday we discussed about microwave catalysis. So in that you said microwave pyrolysis is coming under thermal pyrolysis, thermal plasma category. Now we move to from microwave we also produce cold plasma. From this slide I get it.
No, microwave is not cold plasma. It's a warm plasma. Okay, so it's actually so if you look at today's title, application plasma in ammonia synthesis, I kind of commingle them together just to this slide really. There's still the debate. Microwave, actually the body, okay, let me go back. Where's my? So actually in a DPD cold plasma, electron is hot, and then so in the cold plasma, this species is cold. In microwave, this is not cold. Actually, this temperature can go to very high. It's not it will not be going to be 1400 K, but it's going to be hot enough. Okay, that's different. So that's why they classify microwave as low temperature plasma. It's not non-thermal. They still generate heat just because of interaction between the electromagnetic field with the molecule. You follow me? Yeah.
Yeah.
Yeah. It's in microwave case, it's not. You kick out electron, get plasma, but somehow this molecule, because it all depends on how your molecule align with the electromagnetic field. In cold plasma, because of voltage, there's no alignment. It is really that voltage kick out electron. But microwave there's no voltage. It's a field going in. But when the powerful enough, it does kick out electron. But in the meantime, the remaining part try to align in the electric field, they spin, then they generate heat. So that heat is not that hot, but still it's called a low temperature plasma. You follow me?
Yeah. Yes, sir. Actually, if I send the microwave through vacuum chamber, then automatically it gives plasma.
Yes, it does.
Yeah. Yesterday we used that plasma as the. You said that plasma is not exactly plasma. Actually, in microwave catalysis, we are heating the catalyst through microwave. But here, how we are?
Okay. No, you're confused. No, you're confused with microwave only. Okay. So yesterday we talked about microwave. There's no plasma yesterday. So basically, microwave only when you I see your point. I see how you're struggling. Okay. Yesterday is okay. Let me cue this one. Yesterday we talked about the microwave only. Microwave only means you apply the microwave power but do not generate plasma. It's really microwave interacting with the catalyst. Heating catalyst enable the reaction. But here you generate the plasma using microwave. Microwave can do two things. Microwave do not have to generate plasma. Microwave can interact with the catalyst. But there's another scenario. Microwave can generate plasma and interact. So let's go back. Okay, I see how you are struggling. Yeah, that's why I use the terminology called microwave only, no plasma. Okay, so let me go back. Okay, I'm going to share that. Can you see my slide?
Yeah, yes, sir.
Okay. So if you look at this diagram, there are two scenarios, all right? I use a so-called two optic mode. On the left-hand side, it's a microwave only, no plasma, okay? So basically, in this scenario, microwave interact with catalyst in the gas phase. The methane and the nitrogen come in, there's no plasma. It's a neutral, stable molecule, and then interact with the catalyst. But that catalyst has already activated by the microwave, and then they induce reaction. If you look at the second scenario, same microwave, if you increase the power, this species will become this is the plasma, and then react with the catalyst. You follow me? So
Yes.
yeah, that's a different scenario. You can operate the microwave in different scenario. So so normally when I teach these courses, it's very difficult to teach online. When I teach these courses, actually I bring students in my laboratory. So you go into my laboratory and show them microwave, and also in microwave only, and then the other, where's my, okay, I lost my cursor. Here we go. So in my laboratory, show the microwave only. They see basically it's empty tube with a catalyst in the center. Then I basically start increase the power. Then they can see the pink color. Actually, nitrogen plasma is the pink color. Then they say, well, this is microwave plasma catalysis. You understand what I'm saying?
Yes, sir. I understand.
Yeah.
So if microwave observers are present, means then microwave is converted into heat, or heat observed. If no observant is present, means then plasma will generate, sir. Shall I take like that?
So yeah, in this case, when microwave interacted with this the molecule, I mean with the catalyst. So then catalyst come in, then the heat generated, right? So what's your question? You say when in this case the plasma is hot, or is that what you're saying? Or what's your question?
Yeah, actually, if microwave observant or susceptor is present, means microwave is used for heating. If no susceptor, the medium is vacuum or only nitrogen or some other gas present, then microwave.
Okay, I know what you're saying. Okay, well, so this material. Okay, let's start. Let's begin. So in microwave only, so this is a microwave acceptor, all right? You can heat it. Once you heat it, microwave, and the methane and nitrogen can react. That's clear, all right? You understand what I'm saying? So this material is microwave. Oh man. So in this scenario, the catalyst is a microwave absorber, and then under microwave without plasma, methane nitrogen will react on the surface, all right? Because I'm heated with microwave. You understand what I'm saying, all right? This scenario. Yes. Okay, now go to next scenario. In next scenario, my catalyst is not in the microwave zone. Okay, this microwave zone is here. However, I use microwave to generate the plasma. So this plasma actually is under it's hot. It's not very hot, but the temperature, let's say 200 degrees C. Sorry, when I speak fast, I'm start coughing. So then the plasma landed on the catalyst, and the plasma heat transfer to the catalyst, and also the plasma, because it's pre-activated, also react on the catalyst. In this case, this catalyst does not need to absorb a microwave. You can put a microwave in there, but more like redundancy. In this case, because of the species already pre-activated, your catalyst does not need to be microwave absorber. You understand what I'm saying? Doesn't have to be.
Yes.
It's called afterglow or the post-plasma reaction. So in this case, the scenario in this case, just remember.
Yes, sir.
So
Actually,
you understand, all right? Just you remember. So this scenario is no different from the cold plasma because I pre-activated the molecule, then they landed on the catalyst. Okay. Yeah, you said, oh, why don't I can still heat this with a microwave? Yes, you can, because why you the double dipping? Why you double activate the catalyst? You can put this in the microwave as well. But my point is, in this scenario, the key is I use the microwave to generate plasma. The light plasma interact with the catalyst. Yeah, you follow me?
yes, sir. I got it, sir. In our laboratory, we have a microwave reactor.
Yeah.
We try to generate plasma from that reactor.
Yeah.
With Ventas, who are all expert in microwave manufacturing, microwave reactor manufacturing.
So what gas you use to generate plasma?
We use the nitrogen, sir.
So you under ambient pressure use nitrogen generate plasma?
No, we can't able to achieve that. They said at vacuum condition it will create plasma. If
Yeah.
If the region or if the chamber is filled with any gas, it won't generate plasma.
Yes, under pressure you won't.
Yeah.
So what is your question? You are asking me how to generate microwave plasma with nitrogen?
Yeah, exactly.
Okay. All right, here's how you do it. So basically, okay, now I understand the question. I thought you are asking a question about slides. Now you are asking a question about your laboratory. So that's different question. Okay. So
yeah.
you are trying to asking me question why you in your laboratory under ambient pressure you are not able to generate plasma with the nitrogen. That's the question, all right?
Yeah, how you are generating, because in that picture it shows nitrogen shows plasma. Sorry, microwave is penetrated over the nitrogen. It creates plasma. In that picture, the pink color shows there is a plasma. That plasma is generated at nitrogen condition. So it is not low pressure. At some pressure, at nitrogen atmosphere, your plasma is generated.
So my question is, can you generate a nitrogen plasma without catalyst in the cross tube using microwave? Can you generate the nitrogen do you see pink color nitrogen in your microwave reactor plasma?
Yes, sir.
Under vacuum.
Yeah, under vacuum, that hot plasma. Yesterday we discussed at the time of microwave catalysis. In between the catalyst, there will be the gap. In that gap, we may find colors. That colors indicate that hot plasma or localized plasma may generated in between the catalyst. If microwave is absorbed by susceptor or absorbent, other than those places or that microwave heat other places, it will create hot plasma in between that in between catalysts.
Yes, it will. Okay, it's called the microplasma. Okay, now I understand your question. Okay, let's go. I have to cue the annotation. Yes, you're talking about here, all right? So basically, if you have cut particles, you will have the plasma in this region, but it's called the microplasma. So I don't think you can see with your eyes. You have to have the instrument to see it. Okay. Yeah. Do you have that instrument to see the plasma? You have to have the instrument. It's called the OES. Okay, let me. In order to see the plasma, you have to have instrument. I think it's called OES. I think it's called optical emission spectroscopy. Do you have that in your laboratory?
No, sir. No, we don't have, sir.
Yeah. So my point is, there are two ways to generate using microwave generate plasma. Either you put vacuum or you start with argon. If you want to generate, if you want to create the nitrogen plasma at ambient pressure, not vacuum, you should not start with the nitrogen. You should start with the argon. Argon, you can generate plasma. Once argon plasma generated, then you flow nitrogen. Okay, so that then you start the reaction. So that's a trick you can play. Or you can do this. If you have a particles like a scattered particles, you can put in there and apply the microwave, and then in between the particles, you will see the nitrogen generate plasma. But that plasma is very difficult to see with your eyes. You have to use an instrument called OES. OES can show you those plasma species.
Yeah, yes, sir. Actually, we have thermal plasma setup also, sir, in our laboratory. We generate thermal plasma with the aid of nitrogen as well as with the help of argon also. We tried, but we are not tried with microwave. In microwave, I will give try, sir. Initially, we have to initiate with argon. Later, we have to supply nitrogen.
Yeah, you need to initiate with argon first. Then because once argon the plasma started, because so easy to argon is very easy to generate plasma under microwave. Then you flow nitrogen into it. Yeah, that's the way how you generate plasma. And then, but another scenario shown here is if you have the so-called microwave absorber or catalyst, you will see something like this. You know, the plasma. It's called the localized plasma, or the so-called microplasma. Let me write it down.
Yeah, exactly. I got the answer. Yeah.
You know what I'm saying, all right? So it's basically called microplasma. You follow me? Yeah. Yeah. Either way, it's going to work. Okay. So, yeah. Did I answer your question? Is that your question?
Yeah. Yes, sir. I got the answer, sir. Yeah.
All right. Cool. Okay, where we are now. So I think I really like this class discussion, even if I prepared so many slides and I could not finish, but I want to make sure each slide, each the topic, or each the subject you understand. I'd rather go slow rather than just running through slides. I can run slow slides. You don't understand. I finish my lecture, but that doesn't do anything good. Please ask questions just like this, okay? So I really enjoy the talking like this. Yeah. Okay, let's go back to the here we go. So now we talk about what's a non-thermal plasma, microwave plasma. So very good discussion. All right. So the different way to generate plasma. I think the reason actually I cut and paste this from a paper. The reason this paper put a microwave radio frequency in cold plasma is a little bit confusing, because if you work in a laboratory, microwave radio frequency, they are not cold plasma. They are hot or warm plasma, because but regardless, this paper put them together. So I think there's a lot of debate. My student actually wrote a very good article. It's called the Microwave and the Microwave Plasma Catalysis in I think it's called a Plasma Processing Journal. It's a very good review, and actually her name is Sarojini Tiwari. She's back in India working for Honeywell. So she wrote a very good paper, and then we fight with the reviewer in that paper, because in that paper we did the same thing as shown here. The reviewer keep on saying, no, you have to separate the microwave out. You have to separate microwave because microwave doesn't belong cold plasma. Then we said, okay, what if we say low temperature plasma? The reviewer say, okay, that's okay, but don't say cold plasma, because yeah. All right. So anyway, there's a lot of debate going on in the literature. But if you work in a laboratory, I will share I'm glad that you asked the question. If you work in a laboratory, be careful. In this two scenario, so if you in the cold plasma, I mean, you can if you use a cross tube, okay, you can touch the wall. You can touch the wall, okay, no problem, cobalt. But the microwave plasma, be careful. You cannot touch the wall. It's hot, okay, because it's plasma interacts with the wall, and then and also the plasma try to align with the so-called what do you call that electromagnetic field. It's hot, so it's not cold, okay. So all right, so let's continue. All right, so this cartoon basically again shows you how when you have the nitrogen go to the NOx, you go to the ammonia. Keep in mind, I mean this and we talk about this. You do electrolysis and then you hydrogen ammonia. A lot of people mention I want to correct a concept. Okay, a lot of people ammonia is a hydrogen carrier. Yes, that's correct. Ammonia is also fuel. Okay, ammonia carries hydrogen. You can decompose ammonia into a hydrogen. You can use ammonia as a fuel for aviation fuel, transportation fuel. But do not forget ammonia as a fertilizer. Okay, so because instead of the decomposed ammonia, a lot of the industrial people telling me you can use ammonia directly as a fertilizer. So that's the key. So once you have a renewable power, turn the renewable power into ammonia, don't forget about the fertilizer application. All right, so the cartoon really tell you the different scenario, how you use the ammonia, how you generate ammonia, and then the key here is there's different way to do the ammonia synthesis. A lot of people try to do the so-called ammonia, the bubbling. That means you have basically this the plasma generation in the aqueous phase. In aqueous phase, then you react. I do not like this because it's very difficult to scale up in there. But if you have gas phase reaction, which means DBD, you probably can scale up and then you multiply your reactor. But once you get aqueous phase, it's limited your reaction because your reaction is dependent on the surface area. It's a limited surface area you can use, but you deal with a big vessel of a liquid phase. But there's a different way to handle this, the scale up. But in terms of the is a bubbler reactor or in the reaction at the interface between the liquid and the electrode, there's a lot of debate going on how you scale up this reactor. So I think that industry I would say general industry like the gas solid reaction. That's how you build the petroleum refinery. If you go to refine a petroleum refinery, most of the reactors are gas solid reaction. They really don't like the so-called, this is called a batch reaction. Batch reaction means you have you pre-store the liquid phase and you react, then you have to have the ammonia, the coming out. But in gas solid reaction, you have gas coming in, which is the nitrogen, hydrogen. You have gas coming out, then you do the separation. It's really how you try to commercialize this. I think Dr. Anand asked me to discuss about reactor scale up. I think I will save it up for the future topic because the different way you can scale up a plasma reactor. So far, most of plasma reactor is still in the laboratory. So I'm talking about for ammonia synthesis. For other synthesis, maybe they have a commercial application. For example, they use this type of reactor to kill the bacteria. That's doable. Let me put it this way. If you have a liquid, doesn't have the water, aqueous phase has a bacteria in there. So you can passing through the bacteria, on the bacteria, liquid, and then flowing the liquid in there. But the problem is, if you have a liquid and then the bubbling the ammonia, that's a different scenario. Okay, so they are very successful using cold plasma to do the so-called I would say for the food processing industry, try to kill the bacteria because they have this the what you call the solvent moving around. So they want to I would say what you call it, pre-processing the material and try to kill all the bacteria so that the food will not get contaminated. So there are a lot of applications in the non-catalysis, but for catalysis it's hard because catalysis means if you use catalyst for ammonia synthesis, it's different from non-catalytic process. So, and to say different way, plasma application in catalytic process is new. So it's in the infant state, but for two, it takes time to scale up. Okay, so I think we are about the time, and then we are going to. So the next session today, we have 3 sessions. I think we have break for 30 minutes. After 30 minutes, we are going to talk about the microwave susceptible catalyst design, how we design the microwave catalyst, and then to scale up the microwave reactor. Okay, so that's expertise our group have. As we speak today, we are building 1 ton per day the microwave reactor. So there's a way you design the catalyst, how to scale up the catalyst. So that will be the next session. Okay, so yeah, you can do the 3D printing and then all kind of scale up. So I would like you guys go to take a break for 30 minutes. We will come back. Okay, would that be good? Yeah.
Yes,
so
sir.
Take 30.
Yes, sir. Thank you, sir. We will meet after breaks.
30 minutes, all right? Half an hour.
1 hour.
Yeah, yes, sir. Yes, sir. 30 minutes, half an hour.
Okay, all right. Okay, I will see you after the 30 minutes. Okay.